Check it out now, y'all.
nanoHUB-U, online instruction.
Welcome to module 4.5, and in this module I'd like to talk about this non-local structure. See, so far, like the very first module of this week, we started with this two-terminal spin valve device. And then we talked a lot more about the concepts of the spin, how you represent it, how you manipulate these things, the mathematics behind it. And now we again want to get back to a physical experiment, actually. And what we'll look at is this non-local experiments. As I mentioned in part 1, week 4 of part 1, when we are talking about spins, and where we are talking about spins from a more common sense point of view without all the fancy math that we are doing now. See, at that point I'd argued that, there were these two-terminal devices which were actually practical devices that were being used for reading and writing information. And then there was this whole class of experiments on what I call non-local structures, which are at this time not clearly of any importance from a practical device point of view, but they're very good in terms of clarifying concepts and in terms of understanding the real physics of measuring important parameters like spin flip length and understanding the nature of spin. And the basic structure consists of something like this. You have a channel, a magnetic contact with which you inject spins. And of course, the basic phenomena that allows you to do that is that a magnet has two different interface resistances for the two types of spins. So if you had a magnet pointing this way, then if you looked underneath that magnet, then any spin that is pointing in the direction of the magnet would have a higher electrochemical potential than one that is pointing in the opposite direction. So they would have two different electrochemical potentials. Why is that? Well, because when electrons get injected from here, those in the direction of the magnet have a low interface resistance, and so the voltage drop is less. And so inside, the electrochemical potential is higher. And this potential sort of extends out and gradually dies out because of spin flip processes. So if you looked out there, the electrochemical potentials, you'd see something like this. And if you put a second contact, this second probe, not too far meaning compared to a spin flip length, so that these potentials have not yet died out. You see, if you went very far away, then these two would again come together. And one wouldn't be able to see any difference between the two spins. But as long as we are reasonably close, and that reasonably close depends on what material we are talking about. So in some cases that could be 100 nanometers, in some cases that could be micrometers. Now, so if you're reasonably close then another probe here would measure this potential. And back in part 1, I described to you a simple model for how one could estimate what that potential would be. Okay? And what I'll try to do in this module is we'll now do a more fancy version of that, and it will actually give you a more general result. What I mean by that is, what we've had back in part 1 is that if you put a probe here that's in the same direction as that magnet, then what you do is measure a potential that would be more like the red one. Whereas if this magnet were in the opposite direction, then you'd measure something that's more like the blue one. And the difference is like your spin voltage. But the question you could ask is, what if this magnet is not along it or anti-parallel, but happens to be at some funny direction? What do you see then? And previously, we had no good way of answering that question, you see. But now we have the full mathematical machinery to do that. And that's kind of what I'll do in this module. But let me first remind you how we did this back in part 1 using an elementary picture, you see. So there the argument was something like this. Now let me write this here. That is, we said that, say, somewhere down in this channel here, we have an up potential, the mu up, and you had a down potential, the mu down. Let me use the colors a little bit. So mu down, and this is the mu up. Oops. And this is connected by some conductance, which you call G up. And this is connected by conductance G down to the actual terminal up there. And that terminal, so if you look in this picture here, we are now talking about that terminal 2, this terminal. It's left floating, so it floats to some potential, mu2. So this is the mu2. That would be the picture we had. And the question is, given mu up and mu down, what is the potential that the probe actually floats to? And the argument we used then was, we said, well, the current here and the current here, those two must add up to 0 because this is floating, so current has no place to go. And so you could write G up times mu2 minus mu up. I guess maybe the way I've drawn the convention, I should write mu up minus mu2. So let's say this one, plus G down, mu down minus mu2 must be equal to 0. So those are the two currents that must add up to 0. And with just a little algebra, you could write mu2 is equal to G up, mu up, plus G down, mu down, divided by G up plus G down. So from here is just little algebra to get there. And this is where I think what we had discussed back in part 1 is that instead of up and down, it is often convenient to define an average quantity mu, which is mu up and mu down, plus mu down, half of that, and a spin potential mu, which is equal to the difference between them. And in terms of these, you could write mu up as like mu plus half mu s. So from here, just simple algebra to write mu as the average plus half mu s, and the other one is the average minus half mu s. See? And if you substitute this back there, you'll get a simple relation. That is, instead of this, let me put mu plus half mu s, and instead of this, let me put mu minus a half mu s. And then the result you get, that was your final expression, which is equal to mu plus G up minus G down over G up plus G down times mu s over 2. So this is in a way a recap of what we had done back in part 1, you see. And this quantity is what you could call the polarization of this probe number 2, because the polarization is determined by this difference in the two contact resistances or conductances. You can define either way is this equivalent things. So this is what you call the polarization. So let me just summarize the basic result here. And now what we'll try to do is the quantum version of it. So that basic result, let me write here. And that is that mu2 is equal to mu plus P2 times mu s over 2. That's it. So for a probe with a given polarization P2, this is what you'd measure. If you turn the polarization around, P2 would become like minus P2, and then you'd get mu minus this. And if you looked at the difference, you'd get the spin potential. So now the question is, what if this magnet is in some arbitrary direction? And this is where the machinery that we have developed this week, and I guess in the preceding weeks, this whole NEGF method, it allows you a way to calculate mu2 for arbitrary directions. Okay. Now the way you do it is the following. Now first, one thing I should stress is that, let me just write the current expression first. So if I'm trying to write I2, then it would be like, there's a Q over H, etc. And then there would be the trace of gamma 2 times AF2 minus Gn. So Gn is tells you the condition inside the channel. So previously we were visualizing it as in terms of these two chemical potentials, but now we have this Gn here. And this connection to the probe, that's what we had these two conductances for, that's what is now represented by a gamma. Okay. And what we want to figure out is what would be the corresponding F2 that is needed. F2 that is needed to make this current 0. Now one point I should mention here is that the connection between the F's and the electrochemical potentials. That point I should mention, that if you look at this original structure here, see when you do this calculation at a given energy, usually what you input is the Fermi functions in the different contacts. These contacts which are assumed to be in equilibrium. So you have a F1 here, an FL here, an F2 here, and an FR here. You have all these different Fs at a given energy. On the other hand, when you measure something, you usually relate it to this electrochemical potential. And for low bias, you see the Fs translate in a linear way to potentials. That's because for low bias, you can use this simple linear expansion, which again we discussed back in part 1. And that the idea is that F anywhere, if you look at the deviation from the equilibrium quantity, it is related to the deviation of the chemical potential from the equilibrium quantity by this minus del F0 del E. So at any given energy, the delta F is proportional to the delta mu. So the way I would do it is, if you're doing a low temperature calculation, you stick to a particular energy, then we choose, say, this F. Let's say we choose this F as 0, choose that F as 1, and then find what these other Fs are. So let's say the F2 comes out as 0.1. So what that means is that if the delta F here is 1, then the delta F there would be 0.1. Well, that would also translate to delta mu's. So if the delta mu here is Q times V, the applied voltage, then the delta mu here would be 0.1 times QV. You see? So we can just look at the F's and translate it into mu's. So what I'll be doing is, here, we'll be saying, well, let's make the current 0 and try to find what the F is. And the part that you have to remember is, the F is something which one could compare with whatever answers we got earlier for the mu's, because the F should translate into the mu's. Okay. So now, in order to have the current be 0, what you can see is the trace of gamma 2A times F2, because F2 is not a matrix, it's a number, so I can pull it out of there, should be equal to trace of gamma 2Gn. Okay. And so F2 is equal to, I can take this off from here and divide it. So this is the basic result, that if you have a probe connected locally at a point through a gamma describes this connection of the probe, then the F that you would measure would be trace of gamma 2 Gn divided by trace of gamma 2A. So let me write this up here. So that's the basic result. Now we'll do a little bit of algebra to try to get an answer that looks like this. So the way we have to do this is, first point is, what is gamma 2? So the gamma 2, as we have discussed before, has the form of I plus sigma dot P. Where P2 is the polarization of the contact. And so this is the thing we did in, I think, the second module this week. And at that time, we didn't write it in terms of the polyspin matrices because we hadn't yet introduced that matrix. But the result we got, you can see, could be written in this form. And then there is a constant in front, which I'll call gamma. It doesn't matter what this is because gamma appears in both numerator and denominator. We'll just cancel out anyway. It doesn't matter too much. What about Gn? Well, that's what we did in module 3. We showed that Gn is, like psi dagger and could be written as half of Ni, where N is the number of electrons, plus sigma dot spin. See? Actually, I may have missed a 2 pi that time because usually, Gn is proportional to this psi dagger, but actually it's Gn over 2 pi that's equal to this. So this is really Gn over 2 pi. That's equal to that. Okay. Now what about the density of states? There's this A. As I've mentioned in the NEGF method, the A is like density of states. And again with that factor of 2 pi in there. So there's an A over 2 pi. That's like the density of states. But there again, we should write it as, half of di. Now here what I'm assuming is that this channel is purely non-magnetic. This channel, it could be copper or it could be a semiconductor. It's a purely non-magnetic channel, which means that as far as the density of states is concerned, up and down are much the same. So it's basically an identity matrix. And then D is the total density of states. So half the D is for upspin, the other half is for downspin. So we'll have a half Di. Okay. So these are then the 2 by 2 matrices that describe the quantities that appear here. And now my point is we have to put this in and evaluate those things. Okay. So let's try. And this is where knowing something about the polyspin matrices and their properties, which I went through, I believe, in the tutorial 2. That should be useful. So let's look at the top one. The numerator is like the trace of gamma 2 times Gn. So it's like those two things. Okay, and the 2 pi I'll ignore because there's a 2 pi there and a 2 pi there. It will cancel out anyway. So so you got this. It's like gamma over 2. And then this times that. So I'll write. Let me get a better pen here. This is divided by And now I have the gamma 2 times A, so it's the product of those two things. A doesn't have any particular structures, just identity matrix. So I could write just gamma D over 2 times I plus sigma dot P2. So those are the things that we need to evaluate. Okay. Now the denominator is actually quite easy to evaluate. Why is that? Well, if you look at this is a bunch of matrices. There's the identity matrix, and then there's sigma x, sigma y, sigma z. And the thing, one property to remember about the polyspin matrices is that they all have zero trace. Trace means adding the elements on the diagonal. And whether it's sigma x, sigma y, or sigma z, that gives you 0. So what that means is when I take the trace, this doesn't give you anything. But the trace of the identity matrix, that's of course 1, 0, 0, 1. Diagonal elements are 1, so the trace is just 2. And so, this denominator, when you take the trace, this gives me 2 times gamma d over 2. So overall then, this whole thing will give me just gamma times d. That's it. Okay. Now the numerator requires a little more discussion. Because what you'd get is, you see, when I'm looking at the top, there are these, there's a product of two things, you see. So you have got I plus sigma dot P2 times Ni plus sigma dot S. And when I multiply it out, the first I times this will just give me Ni plus sigma dot S. That's easy. Then when I take the sigma dot P2 times this, I'll get N sigma dot P2 and then the I, so that's it. And then of course the difficult one, which involves two sigmas. So then there is a term which will look like sigma dot P2 times sigma dot S. So this is the quantity whose trace I need. And now the point is, firstly, that when I take the trace, that first one will give me 2n. 2 because trace of the identity matrix is 2 and then there's n. And these will just give me 0. Why? Because trace of any of the polyspin matrices is 0. So those are all zeros. Now this is the one that needs a little more discussion. And this is where one of the identities that's discussed in this tutorial 2 is useful, is that what I showed there is that this quantity sigma dot P2 times sigma dot S, when you have something like this, you can write it as, there's a first term which looks like P2 dot S times I. And then there is another term which is sigma dot something. Now, since I'm going to take the trace, that second term will drop out. So, we could write it, it's actually the cross product of P2 and S, but it's unnecessary because the trace is all 0. It is just this one that will give me a trace, and that will just be 2 times that. So the point is, the trace of this quantity is really just 2 times P2 dot S. So when I put that back in here, then what we'll get is, there's the gamma over 2, and then when I take the trace of all this, what I'll get is 2n plus 2 P2 dot S. So now we can write down the answer. F2 is equal to, on top we have, I guess the gammas will cancel, so you'll have n, let me write it with a red pen here. So you'll have n, 2 cancels, plus P2 dot S divided by D. This is it. So, and as I mentioned earlier, the F2, of course, translates to the actual potential measured at the probe. So what is the potential measured? Well, it would be proportional to this N plus P2 dot S divided by D. Now, N divided by D, that's like total number of electrons divided by total density of states. That's what you could call the average occupation. So N over D is like F. And the second quantity, that's the spin divided by the density of states. That is what we could define as Fs over 2. Like a spin, it would be like the spin occupation or the spin potential. The reason you put a 2 there is that the maximum value of spin you could have is if all the spins were, like you had only up spins and no down spins. In that case, the number of spins would be half of D. Why? Because D, the density of states, is like half up and half down. So if all the spins were up and there were no downs, then the net spin would be D over 2. See? So because of that, when you're defining it, S over D, it is convenient to define it as Fs over 2. So that Fs of 1 corresponds to having only spins of one type. Okay. So now you can compare. You see, now if we just translate Fs into mu's and say that mu2 is equal to mu plus P2 dot mu S over 2. Then you now see the connection between what we had earlier back in part 1. You see, where we were just thinking of up and down, where the magnets could only be collinear. And now what we have done is we have allowed the magnets to be in any arbitrary direction. And what you get is this dot product of the two vectors here. And so if you had a situation then where you just had, say, one electron, or rather if you had all electrons, all of one type of spin, you see, and the other was completely empty, then you see this occupation F, this occupation F would have been like half. And the spin F would be 1, as I just explained. And so what you'd get is half of 1 plus cosine theta, where cosine theta is the angle between the direction of the magnet, so wherever this magnet that you're using to measure, and the direction of the spin inside the channel. So let's say the spin is in this direction, the magnet is in some arbitrary direction, angle is theta, then the potential you measure would look like half 1 plus cosine theta in the case where the channel is just completely polarized, which means you only have spins of one type. And this is like cosine square half theta. And this half, of course, is something I had stressed earlier in part 1 of the course, that usually with photons, you always have, when you have a polarizer and an analyzer, then amount of current that gets through is proportional to cosine squared theta. Whereas with electrons, with the spinners, it's cosine square half theta. Okay? And all this then, of course, the mathematical formalism that we have developed this week kind of allows you to handle this. And it's kind of got these two parts to it. One is the NEGF method, which we discussed in weeks 2 and 3, with no reference to spin because the method itself is perfectly general. And what we introduced this week is the concept of spin, where all matrices became twice as big, essentially. And together you can see that it describes the basic, includes this basic physics of spins and allows us to kind of fill in those things which we couldn't have done using the machinery of part 1, where we said you just have two types of spins, up and down. And with that, you can understand a lot of things, but there are a few things you cannot understand. And one of the examples of that is, I guess I erased that non-local structure that I had drawn here, just to remind you that the problem we were discussing is this non-local structure, where you have where you inject spins here and measure something here. Now, what I just described to you is how you could understand what you measure here as a function of the direction of the magnet. So let's say we inject spins in a certain direction and you gradually turn the magnet. How does the potential change? That's what I just described to you. But there is a whole class of experiments where people keep the magnet fixed but turn the electron itself. That is, you have an electron injected here in this direction. The magnet is in the same direction, which means you think it should measure a fixed potential, but then you do something here that turns the spin. So that by the time it gets here, it's in a different direction. But then what it measures, of course, is still given by this expression that we discussed. The polarization of the magnet, dot product with the spin of the electron, the dot product. And so if you have rotated the spin, that would also show up here. And this is done in different ways. One is using magnetic fields, which is called this Hanle effect, that a magnetic field effectively rotates the spins, as I had mentioned in the last module, actually. And there is another more recent phenomenon where people have seen this done in spin orbit materials. That is, because of a relativistic effect, actually, electrons in solids, especially those involving the heavier elements, see an effective magnetic field, even though there is no external magnetic field. The electric field kind of appears like a magnetic field, and that can cause a spin to rotate as it propagates. And what people have, there are now a couple of experiments showing that a gate voltage here can be used to change the spin orbit coupling and thereby change the amount by which it's rotated. And how you can model all this, that's what is described in the tutorial 4.3 and 4.4. That's the part I'm not going into in my regular lectures, but it's in that homework problem, and it's discussed a little bit in the tutorials.